We're now going to take a look at some special rules to help us find derivatives. These particular ones are the product and quotient rules. Coming up, we'll also look at the chain rule. In the past, we've looked at some pretty simple functions in order to find derivatives. We just used what is called the power rule, a coefficient of x to some power, and found the derivatives of those. And they were all just separated by pluses or minus, nothing else going on. In some of the cases you see here, it's possible to simplify them into the structure of a polynomial. In some cases, it might be maybe a little bit of a mess, and in some cases, it wouldn't be possible at all. So what do? You'll see in some of these, it's two different functions that we could find the derivative of being multiplied together. Like x squared, we could find the derivative of that. Sine of x, we could find the derivative of that. And they're being multiplied. Or e to the x times something we could find the derivative of. And in some cases, we have some division. Polynomial divided by a different polynomial, or polynomial divided by a trigonometric function, an exponential divided by a polynomial, and we can't really simplify these. We're going to use the product and quotient rules in this case. Doesn't really want to let me go on here. Great news. We're going to use the product and quotient rules. Remember that a product means if you're multiplying two different things, what the answer is. So the product rule applies to this first column as some examples of two different functions we could find the derivative of independently times each other. And the quotient rule, the quotient is the answer to a division problem, is when we have two different functions being divided by each other. Looking at the product rule first, in your formula booklet, it's presented as this mess. And when you Google it, you may also see that it looks a little bit scary. It really is not so scary. So they're saying if you have some function y and it's two different functions u and v being multiplied, you can find the derivative of it by having the first function completely normally times the derivative of the second one plus the second one times the derivative of the first one. A simpler way to look at this or write this might be you have this function, it's some function times another one, and you can find the derivative by doing the first thing times the derivative of the second plus the second times the derivative of the first. Because both multiplication and addition are commutative, which means the order doesn't really matter, you could do swap the order of these internally as long as you're doing one function times the derivative of the other and the second function derivative of the first or whatever. I've used some color coding on this example to see how that looks, trying to keep it so that the darker colors are the original pieces and the lighter colors are the corresponding derivatives. I hope it's possible to see. I want to find the derivative of this product, okay? I'm multiplying a polynomial in this case times another polynomial. I'm going to do the first thing times the derivative of the second. So the first purple, the whole thing, times the derivative of the blue, which is just 4, plus the second thing, completely normally, times the derivative of the first. And you could confirm this in this particular case by multiplying it out, finding the derivative of that and comparing it to what happens if you multiply this out. This could be and should be simplified when you're doing this in an exam, but I really just want to emphasize the derivative right now and not the simple algebra, so I'm going to skip that. Here's a function we couldn't simplify, but the derivative is going to be very similar. We're going to do the first thing times the derivative of the second plus the second thing, oops, I wrote it in this order because it doesn't really matter, times the derivative of the first. You could have written sine of x times 2x just to keep that structure in your mind. Because we typically write the 2x in front of it to avoid any ambiguity, I just wrote it in front here. But that's okay because multiplication is commutative. In the last example, we have e to the x times x squared minus 1. The first thing, e to the x, times the derivative of the second plus the second thing times the derivative of the first, which is again e to the x. It does look like I didn't take the derivative, but I did because the derivative of plain old e to the x is e to the x. If you have a coefficient in any of these, it will also just go along. You could tack it onto either piece. I could say like 2e to the x is my first function, and x squared minus 1 is my second function. You often see, especially in e to the x, because the derivative is the same, that they may factor it out and put it in front. That's just an example of how that could be simplified, but again, the other things could be written in different ways, must be written in different ways, perhaps just in order to simplify it. That's all not related to calculus really itself. We now have the quotient rule, which in the formula booklet looks even messier. Here the order matters a little bit more because subtraction is not commutative. It matters if I do 3 minus 5 or 5 minus 3, for example. And division is also not commutative. 6 divided by 2 is not 2 divided by 6. So we do need to keep this a little bit more clear. Still written a little bit more nicely. We have the low times the derivative of the high minus high times the derivative of the low being denominator, high being numerator, all over low squared. My teacher always used to say low d high minus high d low, all over low squared. That's something I will probably say a lot. It just means the denominator, the low, derivative of the high, minus the numerator, the high, d low, derivative of the low, all over the low squared, not the derivative. Here are some examples. The first one, we're going to do low d high minus high d low, all over low squared. There's the low function times the derivative of the high, the numerator, minus the high without the derivative times the derivative of the low, all over low squared. Again, it could be simplified. You definitely should in an exam see what's possible to expand, simplify, cancel. Not going to in this case. What about this function? Low d high minus high d low. Low function times the derivative of the high one minus the high function times the derivative of the low function, all over low squared. Something you do need to be really careful with. I've seen very often that people, if I had, for example, cosine of x in my original function's denominator, and the derivative of that would be negative sine of x, make sure that you're using parentheses to indicate multiplication. You don't want this to say x squared minus sine of x, for example, because it's not. It's times a negative. And that would be something that could very quickly lead to quite a mess. Okay, I know these little tiny mistakes may not feel like a lot, but they could cause big problems as you progress through here. So be very careful. Use too many parentheses if needed in order to err on the side of caution, indicating multiplication and not subtraction, for example. One more function, the low function times the derivative of the high minus the high function times the derivative of the lower one, all over the low squared. You could pull out the e to the x in front of it, simplify that like we did in the product rule. You could expand the denominator, okay? But in terms of the actual quotient rule, this would be how you apply it. And that is the product and quotient rule.